All right, welcome everybody. Today, Thomas Barrett, Orange County native, visits us from UC Santa Barbara, a philosopher of science and physics in particular. We'll be talking about invariance and definability in general relativity. Thomas's family comes today to visit, so take it away.
Thanks. Yeah, thanks for having me. As Luke mentioned, grew up down the road in Irvine, so it's always really nice to be back in Orange County. I weirdly had never been to Chapman until yesterday, so I'm happy to rectify this.
I hope that is the first time, but not the last one.
Yeah, likewise. It's very nice. I like the looking out on the field and stuff like this. So today I'm going to talk about some work that my good friend and colleague J.B. Manchek and I have been doing in the foundations of general relativity. It kind of straddles topics in philosophy of physics and logic. So I am hoping that there is something here for everyone. I have actually a handout that I would like to distribute. The work is somewhat technical, and it would be useful to have definitions and propositions of. So, thank you for helping. Okay, while that's circulating, I'd like to begin with a story, if that's okay. So this is a story about Newton and his bucket. It's a famous story that philosophers often tell. Okay, so Newton famously opposed to rotational phenomena, like a concave surface of water in a rotating bucket, to argue that there was a distinction between absolute motion and mere relative motion. He used this as to motivate his commitment to absolute space. So in particular, he argued that the concave surface of water in a rotating bucket, it can't be explained in terms of mere relative states of motion. If the bucket and the water are in the same rotational state of motion, the concavity will still be there. The surface of the water will still be concave. And so you have to appeal to something other than relative states of motion to account for this, for the concavity. Okay, so he posited absolute space and appealed to the fact that the water is rotating with respect to absolute space to explain its concavity. Okay. So this point about the story is not always emphasized. It is sometimes emphasized, but not always emphasized. But this episode provides an illuminating example of the definability of new structures from old. So absolute space plays its explanatory role for Newton by allowing for a definition of absolute acceleration. In particular, one can define a notion of absolute acceleration from the resources provided by absolute space, absolute time, Newton's notion of absolute time, and his notion of like spatial distance. In modern terms, what one says is the derivative operator of Newtonian spacetime is definable in terms of its spatial metric, temporal metric, and its standard of rest. Okay, this defined notion of absolute acceleration provides Newton with the tools needed to account for rotational phenomena. It's this defined notion of absolute acceleration that allows him to distinguish between the situation where the water in the bucket are rotating and the water is concave, and they're both not rotating with respect to absolute space and water is flat. Okay, this is an example from history of classical spacetime theories, but there are other examples of this phenomenon where a new piece of structure is defined from old pieces of structure. Like math is replete with examples like this, and you'll be familiar with a lot of them. So let me give some of the canonical examples of definability. So if you have a vector space with inner product, that structure suffices to define a norm. So this is no doubt familiar. A vector space with inner product gives rise to inertial lengths of vectors. Another example, a metric space defines its canonical metric topology. So if you have a notion of distance between points in a set, it gives you a notion of continuity on the set. And like a super easy one. If you have a strict order on a set, that gives rise to a notion of partial order, the less than or equal to relation. In this case, the definition of the new piece of structure is contained in the state. It's less than or equal to. And the logicians among us have many other examples in model theory where this phenomenon of definability is well understood. So what I'm going to be concerned with today is one particular domain, and we're going to be investigating definability when it comes to one particular kind of mathematical object. So that is a relativistic spacetime. Okay, so a relativistic spacetime is a pair MG where M is a connected and Hausdorff manifold and G is a smooth metric of Lorentzian signature on the manifold. In this case, too, it's natural to say that a couple of the structures on a relativistic spacetime are defined in terms of the basic structures, like in terms of the metric. There are a couple of canonical examples here, too. So the derivative operator that's associated with the metric, so the piece of structure that allows us to distinguish between geodesics, like non-accelerating curves and accelerating curves, that's definable in terms of the metric, in some sense. All of the curvature structure of the space-time, so the full Riemannian curvature tensor, the Ricci curvature, the Ricci scalar, all of that stuff is in some sense definable in terms of the metric. In particular, it's actually definable in terms of the derivative operator, you want to say. And a bunch of properties that curves through your manifolds might have, like the property of being a time-like curve, the property of being a causal curve, space-like curve, and so on. These are all, in some sense, definable from the metric. Okay. The question that we're going to be asking today is like what the operative notion of definability here is, like what the proper notion of definability in general relativity is. What's the proper notion of definability for relativistic spacetimes? So like I said earlier, definability is very well understood in model theory, in particular in the first order case. There are lots of interesting results that you can prove about it, and many of them have been known for like 100 years. And so the aim here is to extend some of these results and some of the ideas from model theory into the context of relativity. Okay, so what we're going to do actually is we're going to show that there's a hierarchy of notions of definability. And it's essentially like we're going to work our way up a ladder. There's a very weak notion that's natural. There's some reasons to think that this very weak notion can be improved upon by making it stronger. So we'll just walk our way up a ladder of increasing strength notions of definability. And then since I'm employed by a philosophy department, I feel compelled to draw some philosophical conclusions from all of the technical work. So I'm going to do that very briefly at the end. Okay. There are a couple of conclusions about symmetry and structure that you can draw from this work on definability. I'll mention this. Okay, so before I start, I want to mention one quick heuristic. So this will be helpful in what follows when we're talking about definability. This is a useful thing to keep in mind. So you might be tempted to think of the defined structures on a spacetime as the structures that the spacetime comes equipped with. Like they're the structures that come for free given the metric. Like you have the metric and for free you get the curvature structure. Okay. I say one might be tempted to think this because I don't really know what comes equipped with means, but it's a useful heuristic to think about it. These are the structures on the relativistic spacetime that are in some sense buildable in terms of the basic structures, or their abbreviations or shorthands for like things you could express in terms of the metric. That's the intuition. Like the case of the norm on an inner product space, you don't have to lay down a norm on an inner product space. It comes for free given the inner product. Okay.
But sorry, when you speak of space-time, what do you mean? You mean a four-dimensional space of real numbers?
No, I mean this thing. So a pair.
So is a mathematical object or a physical object?
Mathematical object.
Is a mathematical object.
Yeah.
Limited to the 4 dimensions?
I'm not. Okay. No, I'm not limiting to 4 dimensions. I mean, it needs to be at least 2.
Yeah,
but yeah, exactly. But I'm not limiting dimensions. But yeah,
the point of whether was essentially is a mathematical or a physical object.
Yeah, I mean, talk of definability wouldn't make sense. But I mean, it's not that these mathematical objects are without physical significance. So,
That's another story.
yeah.
My worry was exactly, physically speaking, you think it's difficult to understand what does it mean. Okay, now it's clear.
Good. Thanks for asking. Yeah, so if you like this heuristic of thinking of the definable structures as the structures that the spacetime comes equipped with in addition to its metric, they're the ones that come for free on the spacetime, then this investigation into definability is an investigation into what other structures the spacetime comes equipped with, which is of obvious like foundational philosophical significance. Just as a brief advert, in case I always feel the need to try to convince everyone that I'm doing philosophy. So that's my attempt. Then I'll come back later and convince you more when I draw some payoffs. Okay, so here, this is at the top of the handout. I'm going to begin with a few simple varieties of definability. There are 4 varieties that are natural to call implicit definability because they kind of bear close relationships to one another. Okay, so we'll move through 4 varieties of implicit definability of increasing strength. And then because I can't resist the temptation to talk about explicit definability, we're going to talk about that a little bit too. The explicit definability is a more syntactic notion. It's about whether or not the structures can be explicitly built from the metric. Implicit will be a slightly different idea. Okay, so the idea behind each of the varieties of implicit definability is this. A tensor field, we will restrict attention to tensor fields on our spacetime. Other structures, like we can talk about those some other time. The case of tensor fields is tricky enough. A tensor field on a spacetime is implicitly defined in some sense if it's invariant under the symmetries of the spacetime. Okay, so these varieties of implicit definability are all going to be based on this idea. They're going to be made precise by saying what it is, like what this word symmetry means. There are different accounts one might give. When we plug in different accounts of what the symmetries of the spacetime might be, it'll result in different notions of implicit definability. Okay, so this is the aim. Okay, we just need one more definition to get going. And then we'll be able to do everything with this one notion. So if you have 2 relativistic spacetimes, an isometry from the first one to the second one is a diffeomorphism between their underlying manifolds that preserves the metrics in the sense that the pullback of the metric on the second spacetime is the metric on the first spacetime. The intuition is just isometries are maps between the spacetimes that are bijections, preserve smooth manifold structure, and preserve the metric. Okay, so here's the setup. We'll fix a relativistic spacetime and consider a tensor field alpha on its underlying manifold, and then we'll be asking about what the conditions are under which we might say that alpha is defined by the spacetime. Okay, here's the first most natural notion. We'll say that a tensor alpha on M is level 1 implicitly defined by the relativistic spacetime if alpha is preserved under all isometries from the spacetime to itself. Okay, so the idea here is simple. Here we're considering the symmetries of the spacetime to be like global isometries, so diffeomorphisms from M to itself that preserve the metric. We are asking, is alpha also preserved by all of these isometries? If so, it's implicitly defined at level 1 by the relativistic spacetime. The intuition is in level 1 implicitly defined tensor fields, they are tied to the metric in this sense. If a symmetry preserves the metric, it also has to preserve alpha. Like in that sense, they kind of, philosophers might say, they supervene on the metric. Any change in alpha must have corresponded to some change in the metric. Okay.
Are you here trying to make mathematically clear the intuitive idea that you presented before by saying it came for free?
Yes, exactly. Yeah, so there are going to be a number of different ways to make precise a notion of definability. And then we can ask whether it satisfies that desideratum, whether this is capturing exactly those structures that come for free. Yeah, good. We'll get to that in just a sec. It's not. Good. Okay, this is a totally natural starting place. Level one implicit definability is a supernatural notion. It's actually very familiar, and it works very well in situations where the spacetime has a lot of symmetries. So we'll see later, I'll come back to Minkowski spacetime. It works super well in Minkowski spacetime. In fact, every level one implicitly defined tensor field on Minkowski spacetime is in a precise sense explicitly constructible from the metric. So I'll come back and show that later. It's a supernatural notion in highly symmetric situations. So for spacetimes that admit lots of global isometries. And you can prove a lot of super cool results using implicit definability at level one. So my favorite one is David Malaman's 1977 result establishing the non-conventionality of the simultaneity relation in special relativity. He appeals to a notion of level one implicit definability there. Another one, Howard Stein in the late 60s, in his response to Hilary Putnam's argument for eternalism in special relativity. He appeals to a notion of level one implicit definability. Okay, so this is familiar. It's natural. It works super well in cases like Minkowski spacetime, where you have a lot of symmetries. It does not work well in cases where you don't have a lot of global symmetries. So for spacetimes that do not admit very many isometries, like there are not very many diffeomorphisms from their underlying manifold to itself that preserve the metric, there are going to be too many tensor fields that are implicitly defined on at level one on such spacetimes. It only takes a moment to see this, okay? So we can make this intuition precise. So let's say that a spacetime MG is giraffe if it only admits one isometry. Okay, the only isometry of the spacetime, so the only diffeomorphism from its underlying manifold to itself that preserves the metric is the identity map. Okay, the weird name, we call, Manchek and I call these things giraffe because of an example that David Malamant has often used in conversation and correspondence with us. So his example is, it's an example of how to construct a giraffe spacetime, a spacetime with only one isometry in a particularly natural way. You take Minkowski spacetime and you excise from the middle of the spacetime a compact region in the shape of a giraffe. Okay, so like so. So now, because the thing that you've excised from the spacetime is so asymmetric, every point in this new spacetime is going to be determined by its distances from like 2 points on the giraffe, or two-dimensional Minkowski spacetime. 2 points on the giraffe will determine that point, the distances to those 2 points. And so only one map now from the spacetime to itself will be an isometry. Okay.
Isn't this an anti-giraffe?
Yes. So exactly. Good. Thanks. This objection has never been raised. In another paper,
You're welcome.
Yeah, thanks. We should have dealt with this. I can't believe I didn't see this. In another paper, we do construct a stylized giraffe, where we don't excise a giraffe. We leave kind of, it's a little, if you squint and back up far enough, it looks like a giraffe. So this is just an intuitive example. You can build, explicitly construct examples of giraffe spacetimes. There are tons of them. It's not surprising that such things exist. Physicists have known that they exist for a long, long time.
Is the key that it's a asymmetrical distinguished region?
Yeah, like, I mean, imagine if you just chunked out a square or something, you would still have reflections. So the trick is you're trying to kill all the symmetries of Minkowski spacetime. So you have to excise a set that's asymmetric enough to eliminate all of the symmetries that you previously had. Yeah. This example will work well for our purposes. You can explicitly construct such examples, but we don't need to go into the details because it's not surprising that such spacetimes exist. Also, they're incredibly common, so there's a sense in which they're generic. Okay, so we have the following results. So this is a result of tying giraffes to level one implicit definability. It's important in a talk to give a proof orally And if I were listening to this talk, this would be the only proof that I could follow were it given orally. And so this is the only one that I'm going to give orally. It's our only shot, okay? Or it would be my only shot if I were in your position. No doubt you have a better shot than I do. Okay, so here's the result. A spacetime is giraffe if and only if every tensor field on its underlying manifold is level 1 implicitly defined by the spacetime. Okay, so on giraffe spacetimes, every tensor field is level 1 implicitly defined, and that perfectly, like, that corresponds to giraffe spacetimes and just giraffe spacetimes. Okay, the left to right direction is like almost trivial. So suppose your spacetime is giraffe, well then its only isometry is the identity map. Every tensor field is invariant under the identity map because the identity map does nothing. So every tensor field is implicitly defined. Yeah, okay. Right to left direction. We'll do the contrapositive. So suppose your spacetime is not giraffe. Okay, so there is an isometry that maps a point P to a distinct point Q. It's not giraffe, so there's a non-identity isometry, maps P to Q. What we do is we define a scalar field on M that takes different values at P and Q. You know you can do that. It's just standard tools from differential geometry that have been well understood for like 100 years. This isometry that maps P to Q will not preserve this scalar field by construction because it takes different values at P and Q. So not every tensor field on M is level 1 implicitly defined if you're not sure. Okay, good. We'll come back to results that have a very similar structure 2 more times as we move forward. Okay, so if we meditate on this for just a moment, it seems like a mark against level 1 implicit definability. In particular, it feels like level 1 implicit definability is too weak. Too many tensor fields are level 1 implicitly defined on some spacetimes. Okay, let me give an example. So here we see a scalar field whose contours bear a striking resemblance to my toddler's face. Okay, so the contours of the scalar field, when it's 1, it's closer to black. When it's 0, it's the white regions of the spacetime. This is a scalar field on this giraffe spacetime. It is level 1 implicitly defined by the spacetime because every tensor field on the giraffe spacetime is level 1 implicitly defined. We presumably don't want to say that this is defined by the spacetime. I'm coming back to the heuristic. We don't really want to say that this is part of the structure of this giraffe spacetime. We can all agree that my toddler is the most important thing in the world, but his face is not part of the structure of this spacetime. Yeah, okay. Another way to say this is it's hard to see a sense in which this scalar field is buildable from the metric, even though it's left invariant under all the global isometries of your spacetime. Okay, there's another way we can say this, same point, okay? Although there are no global isometries for a giraffe spacetime, there can be plenty of local isometries. So by which I mean, there can be small regions of the spacetime that are very symmetric, okay? So in particular, in a flat and giraffe spacetime, like the one that we've been considering here, it's flat, but it's giraffe. Any 2 points in the spacetime will have neighborhoods that are isometric to one another. That suggests that, well, not every scalar field is going to be left invariant under symmetries between small regions of the spacetime. So that suggests that we don't want to say that they are genuinely invariant under symmetries of the spacetime, at least if we adopt a general enough notion of symmetry. Okay, so this is both suggesting that level 1 is too weak and pointing away to higher levels. The idea is let's expand our notion of symmetry and adopt a more general conception of symmetry, and that can move us to stronger varieties of implicit definability. Okay. Okay, level 2. We're going to kind of settle into a rhythm here with level 1, level 2, and level 3. They're very structurally similar, as you'll appreciate shortly. Okay, so a tensor alpha on M is level 2 implicitly defined by MG, the relativistic spacetime, if for every connected open set in your spacetime, so every region that's connected, all of the isometries from that region to itself preserve alpha. Okay, so let me say one thing about it. Clearly, level 2 implicit definability entails level 1 implicit definability. M is a connected open subset of M. So requiring, as level 2 does, that alpha is invariant under all isometries from connected open subsets of M to itself is requiring, in part, that alpha is invariant under all isometries from MG to itself. Okay, so clearly, level 2 is at least as strong as level 1. Another thing I should mention is we are, in essence, now we've just expanded our conception of symmetry. We're looking at the tensor fields that are left invariant by symmetries of the regions of our space-time instead of symmetries of the entire space-time. So we've just generalized our notion of symmetry. We are requiring invariance under this more general conception of symmetry. And in doing so, we're hoping to arrive at a stronger notion of implicit definability. Okay, so it's at least as strong as level 1. We want to see that it's stronger, right? So we want to see that in particular, there are level 1 implicitly defined tensor fields that are not level 2 implicitly defined. Okay, so there are this Billy scalar field is not level 2 implicitly defined by this spacetime. It was level 1 implicitly defined by spacetime because every tensor field on a giraffe is level 1 implicitly defined. It's not level 2 implicitly defined. How do we see this? Well, we'll take a little region of our spacetime over here that circles his face. And there is a reflection of an open ball that preserves the Minkowski metric but doesn't preserve the Billy field. But now we have upside down Billy. Okay. So this scalar field is not level 2 implicitly defined by the spacetime. It is level 1 implicitly defined. So level 2 is a strictly stronger notion than level 1. Okay. Even so, it seems that level 2 is still too weak. And we can kind of see this by going through an argument that's very similar to the argument we went through on level 1. Okay, there are spacetimes that emit minimal symmetries in the sense required by level 2 also. Okay, so here is another definition. We'll say that a spacetime is locally giraffe if every open connected subset of its underlying manifold only admits one isometry. Okay, so not only is the entire spacetime giraffe, it's giraffes all the way down. All of the regions are giraffes as well. Okay. It is a bit harder to construct spacetimes like this. You can't do it by excising just one giraffe, because in particular, the excising of just one giraffe, open regions of that spacetime actually admit a ton of symmetries. Okay. But such spacetimes exist. As before, we have the following result, tying local giraffeness to level 2 implicit definability. The proof is like exactly analogous to the level 1 in giraffe case, so I'm not going to go through it. Spacetime is locally giraffe if and only if every tensor field on its underlying manifold is level 2 implicitly defined by the spacetime. Okay, so as I said, like you can show that locally giraffe spacetimes exist. This probably isn't super surprising. The idea is if you mess with the metric asymmetrically enough, you can generate a local giraffe. None of the regions are giraffes. You just guarantee that none of the regions are giraffes by messing with the metric in asymmetric ways enough around your spacetime. Perhaps more surprising is the following fact, and we proved this a couple of years ago. There are locally giraffe spacetimes with the following property. They have points P and Q that are distinct, but admit neighborhoods that are isometric. So both of the neighborhoods are giraffe because it's locally giraffe, but they are isometric to one another. Okay. So in other words, there are locally giraffe spacetimes such that different regions are giraffe in the same way, in like structurally similar ways. I'll draw a picture of this in a second, but let me finish going through the argument. This is to motivate why we might want a stronger notion of implicit definability than level 2. Okay, so here's the argument. Every tensor field on this kind of MG, since it's locally giraffe, is level 2 implicitly defined. But this means that there are level 2 implicitly defined scalar fields that take different points at the P and Q, despite the fact that there's a symmetry mapping P to Q. Okay? So this is to say that there is a notion of symmetry according to which some level 2 implicitly defined tensor fields are not invariant under symmetry. If we adopt a more general notion of symmetry, according to which maybe different regions of your spacetime might be mapped to one another, instead of just considering symmetries from one region of a spacetime to itself. Okay? So this is just to say, if we're trying to capture a notion of invariance under symmetry, maybe level 2 doesn't quite do it. So here is an abstract picture of the situation. Like, these things are a little bit difficult to construct, but here's the picture. So locally giraffe spacetime, we have points P and Q admit isometric neighborhoods. So this arrow is representing an isometry between a neighborhood of P and a neighborhood of Q. Of course, those neighborhoods are themselves giraffe because the spacetime is locally giraffe, but they are isometric. Okay, so there is a symmetry here on this spacetime that doesn't necessarily preserve alpha, our scalar field whose contours are represented by the shading in the figure. Okay, so that's just to say, we might be able to adopt a more general notion of symmetry according to which it seems like there's a natural notion of symmetry according to which not all level 2 implicitly defined tensor fields are invariant under symmetry. Right? That's what I say here. So this suggests that we should look for a stronger notion of definability, and again, it like points the way to a stronger notion. Let's just require invariance under symmetry with this more general conception of symmetry. So level 3. We're settling into a rhythm, you guys. This is good. Level 3 is going to be a very similar argument to level 2, in that you're kind of seeing the pattern. Okay, so a tensor alpha is level 3 implicitly defined by relativistic spacetime if now alpha is preserved by all isometries between possibly distinct regions of your spacetime. So whereas at level 2, we were requiring that alpha is preserved under all isometries from a region of the spacetime to itself for every region, we are now requiring instead the weaker thing, that alpha is preserved by every isometry between possibly, I should say the stronger thing, alpha is preserved by every isometry between possibly distinct regions of your spacetime. Okay, so clearly level 3 entails level 2, because level 3 we're considering like more symmetries now, not just symmetries between regions of your spacetime to themselves. We're considering symmetries between possibly distinct regions of our spacetime and requiring invariance under that. That's requiring more than just invariance under symmetries from a region to itself. Okay. We again need to show, though, that level 3 is actually stronger, not just at least as strong. So I want to exhibit a tensor field that is level 2 implicitly defined, but not level 3 implicitly defined. Okay. So in order to do so, we're going to need one more step on this like asymmetry hierarchy. Okay. So we'll say that a spacetime is Heraclitus if for any open sets in the spacetime and any isometry between those open sets, the following two things hold. First, actually, you didn't have two open sets, you just had one open set. And second, you didn't actually have an interesting isometry, it's the identity map. Okay, so this is just to say, this is a fancy way of saying, a spacetime is Heraclitus if the only isometries between open sets in your spacetime are identities. Like the spacetime does not admit any interesting symmetries. It's super, super asymmetric, like as asymmetric as possible. You've messed with the metric in different ways at every point of your spacetime in such a way that not only do no regions exhibit interesting symmetries, but there are no interesting symmetries between distinct regions. Okay. So here is perhaps an illustrative proposition, and it'll help explain why we call these things Heraclitus. So a spacetime is Heraclitus if and only if, for every pair of distinct points in your manifold, pick any neighborhoods of those points, there is no isometry between those neighborhoods that takes the first point to the second point. Okay, so another way to say this, the content of this proposition, is in a Heraclitus spacetime, each pair of distinct points has a different local structure. So like the metrical facts at each point of a spacetime, a Heraclitus spacetime, they're different. Like each open region is different from every other open region. So this is why we call them, I didn't choose this name. I like the name, but I didn't choose it. This was Manchek. So we call these Heraclitus because in such a spacetime, you can't step in the same river twice. Yeah, every point is distinct. Every point has different metrical structure. So Heraclitus spacetimes exist, and they, like giraffe spacetimes, are probably common. Everyone we talk to thinks they're generic. We think they're generic, but it's super hard to show. We haven't shown it, and we haven't seen anyone who has shown it either. The construction is a bit involved of the one that we construct, so I'm not going to go into the details. But it's not surprising that such things exist.
Can I ask a question about that?
Yeah.
How much set theory do you need? Do you need the accident of choice to get these guys?
No. So the paper we build it in is called Holes to Heraclitus. I did not do this construction, and there is no way I could have come up with this construction. But what JB does is he picks a small region of Minkowski spacetime, and he lays down a conformal factor on it that's so asymmetric on this small region. It just changes the structure of the metric at every point in a different way. And so it's then a little bit involved showing that it is in fact Heraclitus, but he does the construction explicitly. So there's no, it's constructive. Yeah.
So it's not clear what you say. So that you show that it's Heraclitus. I am Italian, sorry. Heraclitus is Heraclitus.
Yeah,
I have no other way to pronounce it. So that is Heraclitus space time exists in a constructive way without showing them.
No, we do show. The thing we haven't shown is that they're common, like generic. So there's probably a sense in which most spacetimes are Heraclitus. In some sense, like this is to say they're generic. That's the thing we haven't shown. We definitely have shown that such things exist. Yeah.
This is kind of surprising to me in the sense that on these manifolds, small regions will like eventually appear kind of flat. So I would imagine.
So no region will appear flat. Once you zoom into like the tangent space of
yeah,
then it's looking flat, but no region around a point will be flat. I mean, we know that because it wouldn't even be locally giraffe if that was the case.
Right. I know, but there's only so many ways you can approach flatness.
Well, if that's the way you want to talk about it, then this shows that is wrong.
Yeah.
The existence of Heraclitus spacetimes.
Lots of ways.
Yeah, there are as many ways as you want. I mean, the idea is.
Is there like a dimensional limit? Like, does it only work at a certain dimensional height, or can it?
Well, so let's see. We actually have only constructed one in 2 dimensions, but to be honest, usually the reaction to this is the exact opposite of this reaction. Usually everyone is like, yeah, obviously such things exist. It just is a pain in the butt to construct them. This proposition is probably the best that I can do to like gesture at the idea. Like, yeah, just the metric is different around each point. The OP and OQ, they're never going to be flat, and they're going to differ from. There's not like one way that there's just not one way that you can approach flatness. It's not a directional thing. It's the regions just have different structure, and there are lots of different metrical structures that you might have between regions on a spacetime. Enough to make it Heraclitus. Yeah, thanks. That's a good question. I'm actually happy that someone thinks that people think that this is surprising. It's literally the opposite reaction to what we usually get, and we worked really hard on this. Okay, another, this proposition is unsurprising, though, okay, especially given how we've been arguing in the previous two levels. So a spacetime is Heraclitus if and only if every tensor field on it is level 3 implicitly defined by the spacetime. Okay, so we've seen again, minimal symmetries in the sense required by a level of implicit definability will mean maximal definability power, because every tensor field on a Heraclitus spacetime will be invariant under the symmetries that are required by level 3 implicit definability. Okay. Okay, so this is going back to making precise a point that I made earlier. So when I said that there are locally giraffe spacetimes that nonetheless admit local isometries in a more generalized sense, what I was really saying is there are locally giraffe spacetimes that fail to be Heraclitus. Okay, that's an interesting fact, and it's a little bit hard to show. On such spacetimes, every tensor field is level 2 implicitly defined because they're locally giraffe, but not every tensor field is level 3 implicitly defined because they're not Heraclitus. So level 3 implicit definability is strictly stronger than level 2 implicit definability. Okay, so this picture is a stylized depiction of a local giraffe that's not Heraclitus. On such a spacetime, every tensor field will be level 2 implicitly defined, not every tensor field will be level 3 implicitly defined, so level 3 is a strictly stronger notion than level 2. Okay, let me pause and say some nice things about level 3. I skipped over level 2 because I actually think that level 2 is a little bit gross for reasons that we can talk about if you want, but are not super important. Level 3 is a supernatural notion. And it is very adequate on spacetimes that have a large collection of local isometries, like spacetimes of constant curvature do. Okay, so like level 1 worked really well on Minkowski spacetime, and it works really well on de Sitter and anti-de Sitter spacetimes, level 3 works really well on all spacetimes of constant curvature. So I'm going to come back to this later and make it precise also. But again, there are some reasons why we want even stronger notions of definability, or why one might want. But as we are walking up the ladder, it's becoming harder and harder to motivate the stronger notions. This one is particularly tricky to motivate. The easiest way to motivate it is by presenting level 4, and then I will make a promissory note here that I'll come back later and show you how there are symmetries in a more general sense, according to which not every level 3 implicitly defined tensor field is invariant under these more general symmetries. So I'll do the same kind of argument that I've been doing so far, but it just takes, it's easier to do after I've presented level 4. Okay, so promissory note. We'll do the definition and then we'll come back and motivate it. Okay, so here's a natural way to think of our path from level 1 to level 3, and I've been highlighting this as we go. We've been increasingly broadening our conception of symmetry at each of the steps. At level 1, we looked at the entire spacetime and asked what its symmetries were. At level 2, we zoomed into open regions and asked what the isometries were from those open regions to themselves. At level 3, we looked at distinct open regions and considered isometries between those distinct open regions. We're going to do the same thing here, okay? Here is a proposition that I find helpful in motivating level 4. When I put it up on my computer, it looks like a lot. So I'm going to walk you through this, and hopefully you will find it helpful too. But I'm not sure that you will. If you don't, I have a picture that I'll draw afterwards. Okay. So what I'm going to do here is I'm going to re-describe level 3 implicit definability. So that's all that this proposition does. It's a redescription of level 3 implicit definability in a way that shows that maybe there's a way to require invariance under more symmetries than level 3 does, okay? So we have a relativistic spacetime. We have a tensor field on X, okay? X is our tensor field. The first bullet says our relativistic spacetime level 3 implicitly defines X. The second bullet is the redescription. What the redescription says is there is a way to assign tensor fields to all of the relativistic spacetimes that are isometrically embeddable into MG. So intuitively to all of the regions of MG, all of those spacetimes that are embeddable into MG, in such a way that the following two claims hold. So first, the entire spacetime MG is isometrically embeddable into itself, obviously. We assign the original tensor field X to the entire spacetime. And the second claim or the second thing that holds here, is for every isometric embedding between spacetimes that are isometrically embeddable into MG, the assigned tensor fields are invariant under those isometric embeddings. I should say, if you're looking at the handout, I'm pretty sure I made a typo on this in the handout. I made a typo. Oh, don't look at the handout when I say that. Not very many people were looking at the handout, and then I said that. I saw someone looking at the handout. No, there's a typo with a beta. The thing on the screen is the right thing. I didn't replace all of it. I wanted to find them both. Okay, so the first item is just saying that our spacetime level 3 implicitly defines X. The second item is saying that one can assign a tensor field to each spacetime that can be embedded into our spacetime in such a way that the tensor field we assign to the entire spacetime is the tensor field whose definability we are considering. And this assignment of tensor fields to the smaller spacetimes that live within MG is invariant under the symmetries between those spacetimes. Okay. So here's the promised picture. This is our spacetime that we're considering definability on up in the top right corner. Here's our tensor field X on the spacetime about whose definability we're asking. We can assign level 3 guarantees and is equivalent to a tensor field to all of the spacetimes that live inside of MG in such a way that these assigned tensor fields are invariant under symmetries between the spacetimes that are embeddable in MG. Okay? So here's a way to say this. At level 3, one way to conceptualize what level 3 is required is that there's an assignment of tensors to spacetimes that are isometrically embeddable in our original spacetime that is invariant under symmetry between those spacetimes that are isometrically embeddable in our spacetime. Here's a natural way to extend level 3 then. Require instead that X is part of an assignment of tensors to all spacetimes, not just to spacetimes that are isometrically embeddable in MG, and require that that assigned collection of tensor fields is invariant under symmetry. Okay, so this is kind of delivered a little bit. I'll come back to it again, but this is gesturing at how we might deliver on a promissory note to motivate a higher, stronger notion of definability than level 3. If X were part of an assignment of tensors to all spacetimes that's invariant under symmetries between these spacetimes, that would capture a sense in which X is invariant under a wider collection of symmetries than level 3 requires. Okay, so I think I have another picture. So this is level 3. This is going to be what level 4 does. So we're not just assigning tensor fields to the spacetimes that can be viewed as living inside of MG. We're assigning them to all spacetimes. Those that MG lives inside of, like MG can be embedded into, those that bear no interesting embedding relation to MG, we're assigning tensor fields to all spacetimes in such a way tensor field we assign to MG is just our original tensor field whose definability we're considering, and this assignment is invariant under symmetries between all of these spacetimes. Okay, this is the hardest conceptual shift. Level 3 to level 4 is the trickiest one. It requires kind of a change of perspective that I suppose there are a couple of ways to describe it. So one might say that we're moving to a more categorical perspective. We're looking at the collection of all maps between relativistic spacetimes instead of just maps from a relativistic spacetime to itself. We might say it's like a more holistic notion of definability. We might say it has a modal flavor. You're looking at other ways that other possibilities for how spacetime could be, and considering symmetries between these possibilities to determine definability on our spacetime. Okay, but I actually haven't given the definition of level 4. So here's level 4. Okay, alpha is level 4 implicitly defined by MG if there's an assignment of tensor fields to all spacetimes. So there's a way for us to go and lay down a tensor field on every relativistic spacetime in such a way that the field we lay down on our original spacetime is alpha. And second, every isometric embedding between spacetimes preserves the assigned tensor fields. So this second clause here, this is kind of a way to say that this family beta is invariant under symmetry. The family beta is invariant under symmetry. So another way to say this is alpha is part of a family of tensor fields that's invariant under symmetries between relativistic spacetimes. This second clause is actually well known among geometers. It's sometimes called naturality. It goes back like at least 50 years. So another way to say this is alpha is part of a natural collection of tensor fields on relativistic spacetimes. A collection of tensor fields that's invariant under all of the symmetries between relativistic spacetime. Okay, so it's easy to see, given the proposition that I put up, redescribing level 3 implicit definability, that level 4 entails level 3. Because level 4 is just a generalization of the second clause of that proposition. So clearly level 4 is going to entail level 3. The other direction fails. The converse is not true, and it is not super easy to see. So I'm going to walk through an example. Okay. So level 3 does not entail level 4. I'll describe the counterexample and then draw a picture that's better than the description. Okay, so what we do is we consider a Heraclitus spacetime, so a spacetime that's minimal in terms of symmetries in the sense of level 3, that can be properly extended. So there's another spacetime into which our Heraclitus spacetime can be properly embedded. So a spacetime M prime G prime and a proper isometric embedding of M into M prime. Okay, so you can think of MG as being like the bottom half of M prime G prime. That's how I'm going to draw the picture. Now what we do is we choose a scalar field on MG in such a way that the push forward of the scalar field onto M prime, or onto the region of M prime that's in the image of that, blows up. So it goes to infinity as the boundary of M living in M prime is approached. Okay, so here's our picture. So we have MG, the spacetime is Heraclitus. It's embeddable in this bigger spacetime. So here's where the MG portion lives. We pick a scalar field that approaches infinity as the boundary between M and M prime is approached. Okay. Here are the claims. This scalar field is level 3 implicitly defined, but it's not level 4 implicitly defined by MG. It's easy to see that it's level 3 implicitly defined because the spacetime is Heraclitus, so every tensor field is level 3 implicitly defined. Okay, so we get that for free. It is not level 4 implicitly defined by MG, though. Now here is the reason why. In order for it to be level 4 implicitly defined, we would have to be able to assign a scalar field to every spacetime in such a way that we assigned alpha to this spacetime, and the assignment was invariant under symmetries between all of the spacetimes. So in particular, we would have to assign a scalar field to M prime G prime that was invariant under the symmetries between MG and M prime G prime. Well, F is one of these symmetries. Requiring invariance under F will require that the scalar field we've assigned to M prime G prime equals the push forward of alpha on the bottom half of this spacetime. But no smooth field can do that because this push forward blows up as the boundary is approached. So there is no smooth scalar field on M prime G prime that equals the push forward of alpha on the bottom half. Okay, so it is not level 4 implicitly defined by MG. This also was actually not my argument. This is JB's baby. He was super happy about this. I'll show some cool stuff that I proved later. But this was his favorite thing.
Can you just clarify what you mean when you say embedding? Exactly, like an injective?
Yeah, it's a map such that the image of the spacetime under the map is part of. It has to be injected. I mean, what is the actual? It's an immersion. It preserves the metric. Yeah. The main idea here is the bottom half of M prime G prime is Heraclitus. That's the only important thing. Yeah, good question. Okay, so here's returning to the promissory note from earlier. The reason that we might have wanted to strengthen level 3 is the same kind of reason why we might have wanted to strengthen level 2 and why we might have wanted to strengthen level 1. There's a more general notion of symmetry, according to which not every level 3 implicitly defined tensor field is invariant under symmetry. Intuitively, what we're doing is we're moving to considering all of the maps between relativistic spacetimes. And there's a sense in which not every level 3 implicitly defined tensor field is invariant under all of these maps. Okay, in particular, the field alpha that I described in this counterexample doesn't play nicely with the symmetry that embeds M into M prime. So for this reason, it's natural to think that some level 3 implicitly defined tensors are not invariant under symmetry, at least if we adopt a liberal enough notion of symmetry. Okay. That is isometric invariance between all relativistic spacetimes, not just maps from our spacetime to itself or from parts of our spacetime to itself. Okay, we have our first 4 rungs on the ladder. The next thing I would like to do is I'm going to talk about a notion of of explicit definability. There's a sense in which this diagram does not accurately represent the situation. We are going to make a huge jump from level 4 to strong. Strong really should be pictured like up here. It's much, much, much stronger than level 4. So strong that it is not a good notion of definability. But nonetheless, it allows one to prove some interesting things about the relations between level 1 through level 4. So it's worth taking a brief digression into it. Okay, so here I quote myself from earlier. So in this is the heuristic that I was mentioning right at the beginning. We might be tempted to think of structures defined on a spacetime as those that the spacetime comes equipped with. It's much easier to argue for this heuristic if the notion of definability at play is an explicit notion of definability, like constructability from the metric. That's the notion of definability that is at play. And for example, the first 3 examples that I began with, like the norm is explicitly constructible from the inner product. I can literally write out the norm in terms of the inner product. And so it's natural to think of it as an abbreviation or shorthand. So that's just to say, it's easiest to argue for this heuristic if the operant notion of definability is an explicit notion. We haven't been dealing with explicit notions so far, okay? One way that we could argue for this heuristic in the context of an implicit notion is if we could show that some implicit notion is equivalent to an explicit notion. Okay, so I'm going to explore that. We're not actually going to be able to do that, but we will be able to show that in some restricted contexts, some of these notions of implicit definability are equivalent to a very strong notion of explicit definability. So this is closely tied to some super famous results in model theory that have been well known for like 75 years. They illustrate cases in which implicit definability of some varieties entails a notion of explicit constructibility, like actual definability. You can write out the structure explicitly that defines the new structure. Our next question that I want to talk about is closely related to this kind of project. It is the following. We have our hierarchy of notions of definability. Are there some special circumstances in which the implication relations in the hierarchy can be reversed? So are there some situations where maybe level 1 entails some of the stronger varieties? If so, then those would be situations in which level 1 works works better. Okay, so in order to do this, we need a precise notion of explicit definability. There's one that's natural and floats around. So we'll give it. Like I said, it's way too strong. So I call it strong explicit definability. So alpha is strongly explicitly defined by a relativistic spacetime if alpha is a linear combination of tensor products and contractions of copies of the metric and its inverse. Okay. Here's the intuition. Alpha, if it's strongly explicitly defined by MG, you can explicitly construct it by performing kind of polynomial constructions on the metric. You can take 2 copies of the metric, tape them together. You can take the metric, multiply it by a constant. You can take 2 copies of the metric, tape them together, take 2 copies of the metric, change their index structure, tape them together, subtract them from one another. It's polynomial constructions of the metric and its inverse that are the strongly explicitly defined tensor fields. Let me give a couple of examples. So every constant scalar field on an underlying manifold of a relativistic spacetime is strongly explicitly defined. Why? Well, you take the metric, you take its inverse, you contract them. That gives you a constant. You're guaranteed that that's a constant on a constant field on your manifold. You multiply that by the required constant in order to get alpha. Similarly, scalar multiples of the metric are strongly explicitly defined. Clearly, they are linear combinations of tensor products and contractions of copies of the metric and its inverse. Same up here, linear combination of tensor products and contractions of the metric and its inverse. Here's a maybe more representative example. So this field that bears a close relationship to the curvature tensor on a spacetime of constant curvature is strongly explicit. It's a linear combination of tensor products and contractions of the metric. You don't even need its inverse. Okay. So like I said, it's kind of polynomial constructions using the metric and its inverse are the strongly explicitly defined tensor fields on a relativistic spacetime. Okay, easy proposition. If you have a strongly explicitly defined tensor field on MG, it's level 4 implicitly defined. Okay, so we have at least a strong notion. Why does this hold? Well, strong explicit definition provides a recipe for constructing the tensor field alpha on every spacetime. It's giving you like the polynomial expression of alpha in terms of G and its inverse. You perform that recipe on every spacetime. That gives you the required family of fields on all spacetimes that level 4 is requiring. You're guaranteed that that family is invariant under symmetries between those spacetimes because the basic building blocks, namely G and its inverse, are, and the way in which you're combining them isn't changing this invariance under symmetry, just the linear combinations, tensor products and contractions. Okay, so strong explicit definition entails level 4 implicit definition, but the converse does not hold, and this illustrates why strong explicit definition is too strong. So all fields that are strongly explicitly defined by a relativistic spacetime have to be constant because the metric is constant, its inverse is constant, and you're not going to change constancy by taking tensor products and contractions, scalar multiplying or adding or subtracting or whatever these fields. Okay. So on many spacetimes, the Ricci scalar is not constant, so it will not be strongly explicitly defined by the relativistic spacetime. This is despite the fact that it's level 4 implicitly defined, and it's despite the fact that we probably want to say that the Ricci tensor is part of the structure of a relativistic spacetime. So we've kind of overshot here. This is too strong. There are some structures that we want to say the spacetime comes equipped with, but are not strongly explicitly definable. So wherever the Goldilocks, like whatever the middle point is not, we've gone past it. I don't know whether we had gone past it with level 4. I think no, but we've definitely gone past it now. Okay, so here's the final version of the hierarchy. So the reason that I wanted to go past it is because there are interesting things you can show about the relationship between these 4 guys by appeal to this strong explicit definability notion. So let me give you a couple of these results now. Okay, so first an easy one is a warm-up. This doesn't appeal to strong explicit definability, but it's a warm-up. Okay. So on a Heraclitus spacetime, level 1, level 2, and level 3 implicit definability are all equivalent. It's easy to see. Every tensor field is level 3 implicitly defined because it's a Heraclitus spacetime. Since every Heraclitus spacetime is giraffe, every tensor field is level 1 implicitly defined too. Okay, so level 1, level 2, level 3 all collapse on Heraclitus spacetimes. They amount to the same thing. The bottom part of the hierarchy collapses. Trivial results, but instructive for the kind of results we're going to prove now. So warm up, but we're going to move to something interesting. Okay, so this is definitely a slightly more interesting one. So here we consider a very symmetric spacetime. So let MG be simply connected, geodesically complete, and have constant curvature. There are in essence 3 such spacetimes. It's Minkowski spacetime, de Sitter, and anti-de Sitter. That's all. Very, very symmetric spacetimes. In fact, in some cases, these are called maximally symmetric. A smooth tensor field on M is level 1 implicitly defined if and only if it is strongly explicitly defined by the space-time. Okay, so all of the notions of definability collapse on these supersymmetric spacetimes, Minkowski, de Sitter, anti-de Sitter. So this is to say there actually is no interesting hierarchy in Minkowski spacetime. In Minkowski spacetime, all of these notions of definability are the same. This is why in the special relativistic setting, level 1 works so well, because it's tracking a super strong notion of definability. It's tracking strong explicit definability. So this allows us to make like a little remark. Maybe this is more of a sociological remark. Oh, let me say about this before I go on. So the proof follows from an old result in representation theory that's sometimes called the fundamental theorem of the orthogonal group. It's hard to find a citation to the first place where this thing was proven, but it's well known in representation theory.
Question?
Yeah.
I think this is the first time that I've seen the specific structure of the Lorentzian structure appear to be somewhat playing a role. Like it seems like a lot of the results that you've developed aren't dependent on Lorentzian structure. I might not be correct about that, but
well, I mean, like so you mean the signature of the metric?
Yeah.
Yeah, it's a good question. So let's see. We've only explicitly constructed a Heraclitus space-time in 2 dimensions with Lorentzian signature. No doubt a Riemannian analog exists.
I guess they all fall under Lorentzian. It's more of a generalization. You can have the negatives that go.
Well, so not the way that we're thinking about it. We're fixing the signature of the metric to be 1, 3.
Oh, so it's not a
One
higher
minus.
dimension. It's 4-dimensional.
1 at minus.
And they're all 4-dimensional?
No, in fact, our only, like I was saying earlier, the only Heraclitus spacetime we've explicitly built has 2 dimensions. You know, we're like super confident that one exists in 4 dimensions, but they're messy. And so we haven't explicitly built.
Okay. And then so you have 1 negative.
Yeah.
Oh,
Yeah. It is an interesting question. A lot of the definitions will move over naturally to other geometric contexts. Like we're just talking about invariance of tensor fields under smooth maps. So there's nothing wrong with defining isometries for Riemannian manifolds also. One could do that. I imagine a lot of the same results will go through, but you'll need different examples to construct them. Yeah, even here, the one thing that's unique, I suppose, I guess even here, I don't think it's a good question. I'll think about it more. Even here, there's probably a sense in which an analog of this holds in the Riemannian case. It's just that the 3 things won't be Minkowski spacetime, de Sitter spacetime, and anti-de Sitter spacetime. It'll be Euclidean space, the hyperbolic analog of the sphere. Okay, so here is the note that I. So Garrosh and Horowitz mentioned in their Global Structure of Spacetime Long manuscript from the late 70s. They said that we're still somewhat over-conditioned to Minkowski spacetime. And I would submit we're still somewhat over-conditioned to Minkowski spacetime. A lot of the intuitions that we have, I'll speak for myself, a lot of the intuitions I have about spacetime piggyback on intuitions about the Minkowski case. The equivalence of level 1 and strong explicit definition in Minkowski spacetime offers a kind of sociological explanation for why we haven't fashioned varieties of implicit definability that are stronger than level 1. Level 1 works super well in the Minkowskian setting. It tracks a super strong notion of definability. It does not work well when you move outside the Minkowski set. In the Minkowski setting, there is no interesting hierarchy. It all collapses. So you have to move outside the Minkowski setting to see the interesting hierarchy. Okay, this one is my favorite proposition. As I suggested earlier, maybe my co-author and I, our favorite propositions are perhaps a little bit sensitive to which ones we ourselves prove. Yeah. But I really like this proposition. Okay, so let MG be a spacetime. The following 2 things are equivalent. So first, MG has constant curvature. Second, level 3 implicit definition on MG entails strong explicit definition on MG. Okay, so this is delivering on what I said earlier about level 3 working really well on spacetimes of constant curvature. The one entails 2 direction just says on spacetimes of constant curvature, level 3, level 4, and explicit definition collapse. They're all the same thing. Level 3 is perfectly tracking a strong explicit definition. The 2 entails 1 direction is actually the direction that I think is cooler. So what 2 entails 1 is telling us is that spacetimes of constant curvature are completely characterized by this definability fact, by the fact that strong explicit definition and level 3 coincide, telling you that alone completely characterizes spacetimes of constant curvature. I just think that's super cool. We have a definability style result that characterizes this class of like very symmetric spacetimes. It's like, yeah, I just think it's super cool. And the morning that I proved this was a really good morning. Okay. So 3 interesting situations in which the implications in our hierarchy can be collapsed or reversed. So first, in Heraclitus spacetimes, the bottom part of the hierarchy collapses. Levels 1, 2, and 3 are the same. In spacetimes of constant curvature, the top part collapses. Level 3, 4, and strong explicit are the same. And in Minkowski spacetime and de Sitter and anti-de Sitter, the entire hierarchy collapses. There is no interesting hierarchy in those cases because the spacetimes are so symmetric. They admit so many global isometries that the invariance under global isometry is just capturing a ton. There aren't that many fields that are invariant under all the global isometries of Minkowski, de Sitter, or anti-de Sitter space. Okay, so some open questions. We don't have answers to these. So you'll have noticed that we didn't go through the same rhythm on level 4 as we went through on level 1, 2, and 3. That's because we don't know whether we can. So this is the second question. Is there an analog of giraffe, locally giraffe, Heraclitus spacetimes for level 4 implicit definition? We don't know. So in other words, the question is, are there spacetimes that level 4 implicitly define all tensor fields on their underlying manifold? We don't know. The first open question listed is there a weaker variety of explicit definition that's equivalent to level 4 implicit definition? I mean, a good question is there a weaker variety of explicit definition? I think yes. It's a bit harder to write it out, but probably yes. And then is that actually the same as level 4? We don't know. In particular, because we haven't written out a weaker variety of explicit definition. If I had to guess, I would guess yes with 2 question marks and then yes with 1 question mark. But the number of question marks keeps changing, and actually one of the answers changed from yes to no like last week, and I can't remember which one it was. So that's just to indicate like, I don't know, on these 2 questions. Okay, a couple of payoffs, quick. So I want to discuss 2 kinds of philosophical payoffs of all this, tying these definability results to some current debates in philosophy about symmetry, the significance of symmetry and structure. Okay, so the first has to do with some recent attempts to use symmetry to compare amounts of structure between theories, between mathematical objects. I'll discuss this one very quickly. So it's sometimes suggested by philosophers that all other things equal, we should prefer theories that posit less structure. It's structural parsimony principle. For example, we can account for the phenomena, or we could account for the phenomena using the Galilean theory of spacetime just as well as one could account for the phenomena using the more structured Newtonian spacetime. Newtonian spacetime comes with a privileged notion of rest. Galilean spacetime does not. Galilean spacetime is less structured, but you can account for the phenomena equally well. We should prefer it over its Newtonian analog. Okay. The question then becomes how to compare amounts of structure between theories, between spacetimes. This criterion has been floated, and it's become something of a standard tool in philosophy of physics discussions of amounts of structure in the last decade. So it goes by the name sim star. Here is the criterion. X has at least as much structure as Y if and only if the group of symmetries of X is a subset of the group of symmetries of Y. The automorphism group of X is a subset of the automorphism group of Y. The basic idea is that if an object has more symmetries in the sense that it has a larger automorphism group, it should have less structure. Why? Because symmetries are structure preserving maps. So more symmetries should indicate that there was less stuff there restricted. Okay. SimStar makes intuitive verdicts in easy cases of structural comparison. So a topological space has at least as much structure as its underlying set, but usually not vice versa. A relativistic spacetime has more structure than its underlying manifold. That is to say, at least as much structure as its underlying manifold, but not vice versa. And so on. Now, one can show that SimStar bears a close relationship to definability. In particular, this is essentially a trivial result. If we have a spacetime and a tensor field on its underlying manifold, the following two things are equivalent. So first, the original spacetime has at least as much structure as the spacetime once we've added alpha to its structure, according to SimStar. Second, the relativistic spacetime implicitly defines at level 1 alpha. Okay, so what this is saying is when applied in the context of general relativity, SimStar is just capturing facts about which fields are and are not level 1 implicitly defined in terms of the relativistic spacetime. Okay. Of course, and this has been recognized, this opens SimStar up to criticism. So on a giraffe spacetime, for example, every tensor field you add to it results in no more structure, even though we might want to say that some of those fields, like the Billy field, did not come equipped on the relativistic spacetime in the first place, and so adding them should result in a more structured spacetime. Okay. So the connection between SimStar and definability opens SimStar up to criticism. The weaknesses of level 1 permeate to SimStar. Okay. For our purposes here, the interesting thing is that this kind of proposition, tying definability to criteria for comparing amounts of structure, suggests a recipe for fashioning new criteria for comparing amounts of structure. So in particular, the idea is this. We can say that X has at least as much structure as Y if and only if X defines all of the structures of Y, where we plug in for defines one of these notions of definability. So at level 1, we've seen you get SimStar. At level 3, you get a criterion that goes in the literature by the name SimStar 2. It's like SimStar, but where one takes into account local symmetries, not just global symmetries. At level 4, one arrives at some category theoretic tools for comparing amounts of structure that trace back to John Baez 2004. I'm not going to go through the details here, but the important thing for our purposes is that one of the conclusions we should draw is that this debate about how to compare amounts of structure should be happening in parallel with considerations about definability. A criterion for comparing amounts of structure will stand or fall on the basis of how good the notion of definability is it's appealing to. So for example, SimStar is making bad verdicts because level 1 implicit definability is too weak. If we were able to show that level 4 was an adequate notion of definability in general, then the criterion for comparing amounts of structure that it leads one to, we would have an argument in favor of. Okay. All of this is just to say these debates should be happening in parallel. We should be talking about definability when we're talking about comparing amounts of structure. Okay, so I want to turn to a slightly different question, still related to symmetry and structure, but now having to do with the idea that one can use symmetries to present an entire structure, an entire space-time structure, not just to gauge the amount of structure that the object has. So here's a famous quote that's, you essentially have to say, you have to put this up anytime you talk about symmetry and structure. File said something about symmetry and structure. Symmetry is useful when thinking about structure. Here it is. This idea has been emphasized more recently by philosophers of physics. So David Wallace has recently proposed that you can present some space-time structures by singling out their privileged collections of coordinates and looking to the fields that are invariant under transformations between these privileged coordinates. That's a way of using symmetries, so symmetries, transformations between privileged coordinates, to present a space-time structure. Jill North, in her recent book, has put forward similar ideas about coordinates and symmetries and their significance for gauging structures of the objects that we employ in our best physical theories. We can contribute a few small positive results to this topic here. In particular, the results we've proven about the implications in the hierarchy being reversible allow us to illustrate a few cases where symmetries actually do perfectly encode structure. Okay. So here's one way to ask the question. How much of the structure of a relativistic spacetime is encoded by symmetries? Suppose in particular that two spacetimes have the same symmetries, in some sense of symmetry. We can then ask, are they structurally identical? If yes, that's obviously a case in which symmetries determine structure. If no, it's a case in which they don't. Okay.
Question.
Yeah.
Can we not ask how much, what notion of symmetry would fully determine the structure?
If there's,
It might depend, it might vary, but if there's generally a way to say that there exists some specification of symmetries that fully determines the structure,
Yeah.
then you could say, let's take the minimum that fully determines the structure.
Yes. So that's essentially the question that we're going to be working through here, is plug in different things for your notion of symmetry and ask this question. On some of the less general conceptions of symmetry, the answer is going to be no. So here, I'll show you those ones. So there are non-isometric spacetimes that admit the same global symmetry. So the same symmetries in the sense considered by level 1 implicit definability. That's more or less obvious. Take any two giraffe spacetimes that have the same underlying manifold. They have the same automorphism. They admit the same global symmetries. They can be radically structurally different, though. They're not guaranteed to be isometric. They are not even guaranteed to be conformally equivalent. Like, they can be super, super different. Just their structure is very asymmetric. That's all that's required. Okay. Also, there are non-isometric spacetimes with the same local symmetries. Take any two Heraclitus spacetimes that are not isometric. They're going to admit the same local symmetries, but they can be very structurally different as well. Okay. So this is to say, in Luke's way of thinking about it, the notion of symmetry required at level 1 doesn't in general determine structure, at least in all cases. Notion of symmetry required at level 3 doesn't in general determine structure in all cases. But what we can show is there are some special cases where these notions of symmetry, not even broadening these notions, but these ones actually do work. Okay, and these are the things that are going to follow from as corollaries to the results that we proved about the implications in the hierarchy being reversible. So here's the first one. Suppose you have a simply connected geodesically complete spacetime with constant curvature. So that is to say, Minkowski de Sitter or anti-de Sitter spacetime. If you're given another spacetime over the same underlying manifold that admits the same global symmetries, that is to say, it has the same isometry group as our original spacetime, the two metrics are related by a scalar multiple of one another. Okay, this follows from the proposition we proved about level 1 implicit definability entailing strong explicit definability in spacetimes like this. Okay, so this is to say, on Minkowski de Sitter, anti-de Sitter spacetime, those spacetimes are determined by their isometry group up to a choice of unit for the metric, like up to homothety, one might say. You can't tell me what the metric is exactly, or up to isometry, but you can tell me up to a choice of unit, which is really good. That's a lot. I mean, that's as much as we probably want. As a corollary to this, if you just think about Minkowski spacetime, if you have a spacetime with the same isometry group as Minkowski spacetime, actually the two are isometric. So not just related by constant multiple of their metrics, they're literally isometric. Okay. And the third recovery results. Well, this is just to say this. Minkowski spacetimes completely determine my symmetries up to isometry. Third recovery result, take a spacetime with constant curvature. Suppose you have another spacetime that has the same local symmetry, so the same symmetries in the sense required by level 3 implicit definability. One way that people sometimes will say this is the same isometry pseudogroup. then the two spacetimes, again, are related by constant multiple, a constant scalar factor. Their metrics are related by a constant scalar factor. So this is just to say spacetimes with constant curvature are determined up to homothety by their local symmetries, not necessarily by their global symmetries, because constant curvature spacetimes can still be Dirac, right? So they're not determined by their global symmetries, but they are determined up to homothety by their local symmetries. Okay, so given these recovery results, what can we say about the question that we started with? What's the significance of symmetry in general relativity? Does symmetry determine structure? I don't know. We've seen a few cases where it does not. Actually, a lot of cases in which it does not, insofar as Dirac spacetimes and Heraclitus spacetimes are common. We've seen a few special cases where it does. So yes and no. A lot turns on how general a conception of symmetry one has. If we have a very narrow conception of symmetry like that required by level 1, not a lot of spacetimes are determined by their symmetries. If we move to level 3, more are, but still, there are lots of Heraclitus spacetimes, one conjectures. So the answer to this question depends on how general conception of symmetry one is employing. One thing I will remark on here is all of the recovery results I just talked about were at levels 1 or 3. We don't have any recovery results yet at level 4. Insofar as level 4 is a stronger notion of implicit definability than levels 1 through 3, the kind of recovery results one could prove will be stronger than the kind of recovery results that one could prove at levels 1, 2, and 3. We don't have any results yet, but insofar as one could prove them, they will be better than the recovery results that I have so far. So a lot depends on how general a conception of symmetry one has and on what kind of recovery results one can prove at level 4. Okay. So I'm going to end there. Thank you so much. Breeze, 2, 3.
Okay,
Let's start with breeze.
an early implementation of the notion of geometric invariance into logic has given rise to the so-called abstract Galois theory.
Yeah.
And my question is whether that could be applied to your setting. Take any subgroup of all of the group of all local isometries of the Riemannian manifold, and assign to it the set of all tensor fields that are left invariant under the action of that group, and conversely take a system of tensor fields and assign to it the subgroup of all the local isometries, leaving it invariant. So you have two functors basically, and so you can look at the composition of the two functors. And one question is whether, given any subgroup of the group of all local isometries, there is exactly one system of tensor fields which is left invariant.
Yeah, that's a recovery result. If
that is the completeness result on the scale of the space-time manifold that you're dealing with.
Yeah.
So that's true.
I don't know.
Oh, okay.
Yeah, you know.
No, I know that there's an abstract result in the field of logic. I mean, about first-order logic, first-order structures.
Yeah.
But my question is whether you can apply the same question to your setting and whether
the answers are the same.
There is a result.
I don't know. I mean, I know you probably know this stuff better than I do, but I know that, I mean, some of the definability results, even in the first order case, don't generalize to like the second order.
No.
So it wouldn't be surprising if they don't generalize here.
Yeah.
But I don't know the answer.
But you could single out, delineate a special class of complete manifolds in the sense that they give rise to that kind of correspondence.
Yeah. Yeah, it's a good way to approach it. I'll think about this more. I mean, definitely these kinds of tools are relevant. Like the way that they're a lot of the results about reversing the implications in the hierarchy are corollaries of results in representation theory. So it's not surprising at all that this stuff comes into contact. And it wouldn't surprise me if stronger results in representation theory are adjacent. areas let us prove stronger results here, but I don't know the answer.
And just on a more general note, it looks like you're told if this is some kind of backlash of logic onto physics, because if you think of invariance and definability in logic, it was basically inspired by Erlangen, Klein's Erlangen program, which itself was, at least to some extent, inspired by physics. And so it likes the loop is, it loops a loop, because then there's some kind of motivation from logic.
Yeah, that's right.
Physics.
I mean, one way that philosophers of physics will tell the story is like the Kleinian program worked very well for classical spacetimes, like Newtonian spacetime, Galilean spacetime. They're determined by their isometry group. It works very well in the special relativistic case too, as like these recovery results are illustrating. And then it breaks down in the move to general relativity because, and so then essentially what we're asking here is whether there's a more general way of thinking of the Kleinian program, like think of more symmetries than just global symmetries. Like think of symmetries, but you have other symmetries at hand, use them. And the question then is whether this expanded Kleinian program allows you to treat even the general relativistic case, like the normal Kleinian program allowed you to treat the classical spacetimes and special relativity. Yeah, totally agree. It's a good way to conceptualize it.
Thank you.
Luke? Is there a notion of partial definability? Like the what I have in mind is if you have a gauge potential, it implicitly defines a gauge field that's invariant under whatever the symmetrics are of your gauge. But if you're given an invariant gauge field, the Faraday tensor, then it will partially determine your gauge potential up to some freedom. And this sort of partial determination seems to be a fruitful.
I don't know. I would conceptualize that case slightly differently, I think. So one thing you can say is, you're definitely right, given a potential, you can define the Faraday tensor, you can define a choice of gauge. There is a notion of partial definability going in the other direction. If you're given the Faraday tensor and a choice of gauge, then you get the potential back. So in essence, what you're doing is you're saying, once I have the Faraday tensor plus some more structure, I can define.
Right, it's the characterizing what's the extra structure that you need to get back. I think that's useful. Being able to characterize what exactly that remaining information is.
What the surplus stuff is. It's not going to fall out easily from this, but I can see the connection. I don't have a good answer. Guillaume?
Thanks. I think I have a question about the definition of level 4.
Okay.
Definition. So the way you define this, right, you have this requirement that you have to associate a particular vector field to every spacetime, right?
Yeah, a tensor field, it's going to be of the same rank, same index structure as the alpha that you're considering.
So it seems to me that this definition is sort of, you could phrase it equivalently if instead of requiring it for every spacetime, you would just look at those spacetimes to which the original one embeds.
And the ones that are embeddable.
Yeah, sure. Yeah. So basically everything that is connected to the original one in terms of embeddability.
I don't know. It feels like it should be equivalent, because how could what's going on elsewhere affect?
Right.
It feels like it should be equivalent.
Your counterexample was exactly that, right? So you embed it into something bigger.
Yeah, exactly. The counterexample we used to show that level 3 doesn't entail level 4 just considers a close spacetime to the one that we're considering, one that it can be embedded in. So that counterexample would still go through on your notion, but that isn't to say that your notion is equivalent to, it's just to say that your notion is also stronger than level 3, right?
Right. But
I don't know the answer to whether or not they're equivalent. I share your intuition.
Right. It sounds like it should be, because if it's not connected to the original space in terms of embeddability, you could take some like trivial.
Yeah.
You have to fill in the missing dots, right? Which is like something like trivial.
Yeah. I mean, this notion of definability, one thing I'll say that I don't know the answer to the question. I share your intuition. I don't know the answer to the question. one thing that you might say in favor of it is it has a very modal flavor, like you're looking to other nearby possibilities to your MG. Not at all space-times,
Right,
like
yeah.
those that are super far away and have no interesting relation to MG whatsoever. You're just looking at the nearby guys, the guys into which MG can be embedded, and the guys that can be embedded into MG. Yeah, I'll think about it.
Right. I think it also gives you kind of like a natural progression from type 1 to type 3, right? Where you look at type 3, you look at embeddable things, and then you look at things into which you embed.
Yeah.
And that's about it, right?
Yeah, I mean, the one worry is that it does then feel like requiring what we're requiring on level 4 is requiring invariance under more symmetry. Because you're considering all the other structure preserving maps between relativistic spacetimes. So let me say one other thing about level 4 that I didn't say here, but one thing that's nice about it. So suppose you have some like uniform variety of explicit definability. Okay, so it would be a mark in favor of a condition of implicit definability, at least I take it, if it's equivalent to some variety of explicit definability. If you have a kind of uniform variety of explicit definability, so that is a variety that provides a recipe for constructing the field on every space-time, like strong explicit definability does, then it's going to entail level 4. So that means that if you want a notion of implicit definability that's equivalent to a notion of explicit definability that's uniform, you need to go at least as high as level 4. Your notion might do that too, but I don't know. Yeah, I'd be interested to see a proof.
Can I just follow up? Yeah. I mean, so because one thing that sort of that I find a little puzzling, right, with this current definition of level 4, right, is that so and maybe this is also because I'm coming more from the side of logic. So I was a bit surprised that your notion of definability was relative to a particular spacetime and not to the signature, the theory of spacetime. Right?
Yeah,
so,
you don't have, yes. Continue.
Yeah, because if you think about examples of definability in the case of like, like the Beth definability, right? So this is a criterion that is stated in terms of like theories, right? Where you look at all models and then redux of these models, right?
Yeah.
You can basically, the idea being that if you have like an isomorphism of the reduced language and you can lift it, right?
Yeah.
So have you looked at any sort of analogous sort of criterion there?
Yes, so that's in fact one of the things that's motivated level 4. So another way to state the variety of implicit definability that's at play in Beck's theorem, it's normally stated in terms of looking at redux of models, and if the redux are equal, then the models were equal. Another equivalent way to state that is the new language is left invariant under all of the elementary embeddings between models of the theory. That's equivalent to the reduct version of implicit definability. So one way to state Beck's theorem is explicit definability if and only if invariance under all of your elementary embeddings between models of the theory. And that looks a lot like this notion of level 4. So like, that's kind of the thing we're after. This is closer to, this is part of the reason why the jump from level 3 to level 4 is conceptually difficult, is because we kind of have changed the question from the question you were saying, like, focus on one relativistic spacetime and ask what's definable on it versus focus on what's definable on relativistic spacetimes. In essence, what we're doing here is that second condition in level 4 is a claim about which assignments of tensor fields are definable on relativistic spacetimes. Like natural assignments that are invariant under isometric embeddings between spacetimes, those are the families that are definable, which is super close to asking which language elements, like in the first order case, are definable. Because we're not talking about a particular model anymore. We're talking about assignments of tensor fields to all of your models. Like talking about an element of your signature is talking about assignments of, extensions to all of your models. So like these are the things that we're motivated by, but I agree that it is ugly and it's hard to motivate this notion of level 4. And it would be nice to have an easier, a cleaner way to say it.
Thanks.
Yeah, thanks. That's super helpful.
Amen, please.
When you consider the time, is the time exists or the time
of philosopher. I'm thinking about the debate of 1922 between Bergson and Einstein. Which time you consider?
Wait, hold on. Say the first half of the question again. I didn't hear the first half.
I'm considering the time. Which time you are considering? The time of physicist or the time of philosopher?
I don't know.
Because there was some
Neither.
famous debate between Bergson and Einstein on this point.
I don't think I used the word time. I thought it in my head when I was thinking I'm going too long. But yeah, I'm not sure. Maybe we can talk more. I'm not sure if I see how the Bergson Einstein thing. I don't want to take a stand on that. If I am, that would be surprising to me because I'm certainly not trying to. But it's an interesting connection.
And another question is, do you have some local global principle here?
Good question. So whenever I've used the word global or local, I've tried to put it in scare quotes. What I mean by a global symmetry is I don't have a general global local distinction. All I mean by global symmetry is a isometry from your entire relativistic spacetime to itself. So like a diffeomorphism from the entire manifold to itself. A local symmetry, well, there were kind of two different notions, the notion required by level 2 and the notion required by level 3. Intuitively, symmetries between parts of your spacetime. But that's it. I didn't want to take a stand on any general thing there. Yeah, thanks. James?
So an extremely important tensor is the Einstein tensor. So I'm wondering if it's known whether the Einstein tensor is level 4 specifically, the level of definability.
Well, so yeah, it should be under all of. It's not going.
This basically encodes the idea of a natural tensor constructed a metric.
Yeah, that's right. So wait, so tell me exactly how you're thinking of the Einstein tensor. So what is the Einstein tensor?
But it's constructed from the by contraction on the Ricci tensor.
Yes. So the Ricci, yeah, the Ricci tensor is level 4 implicitly defined.
Okay.
It's not always strongly explicitly defined. It's strongly explicitly defined only on spacetimes of constant curvature.
And Riemann curvature tensor is also
Strong level 4. But I mean, yes, it's level 4. So the family of tensor fields you consider is the family of Riemann curvature tensors on all relativistic spacetimes. The family of tensor fields you consider to show that the Ricci curvature is the level 4 implicitly defined is the Ricci curvature on every relativistic spacetime. So Ricci curvature is level 4 implicitly defined. So insofar as the Einstein tensor is related to the Ricci curvature by like a scalar multiple and some contractions, it is too. Yeah. How you would do it is what we're requiring at level 4 is that there's like a recipe that you can do on every spacetime. This family of tensor fields beta is the recipe you can do on each spacetime.
So if you have a confirmed natural tensor, you only perform natural operations on it, then what you obtain from that
Is level 4. Yeah, that's good, right?
Yeah.
Like it would be bad. Yeah, if so strong explicit definability has gone too far because some tensor fields like this are no longer definable. I'll take the opportunity to just say one thing about like a potential way to weaken strong explicit definability. Strong explicit definability was only enabling you to do things with the metric, but that's not what you do. You also do things with the derivative operator. Like in fact, how you build the curvature tensors is in terms of the derivative operator, not in terms of the metric. You can build it with the metric on spacetimes of constant curvature, but you can't do so in general without using the derivative operator. So a natural way to try to weaken strong explicit definability is by allowing yourself use of the derivative operator too. It's just a little bit hard to write it down. Explicit definability is just really hard, you guys. Like you don't have a language in general relativity. In the first order, like in model theory, you have your signature, you have your language, you know like what the basic ingredients are. And you also have your building blocks for building from the basic ingredient, like construction principles. Here we have like kind of an intuitive idea about what the constructive principles are. We have an intuitive idea about what the building blocks are, but they're not like given to you on a plate like they are in the model theory case where you have a fixed language. Yeah, good question.
Yeah. Thank you very much for the talk. I don't know if you've heard about this work on locally covariant field theories or quantum field theories, but it made me think of something that might count as another motivation for level 4 definability. Is that they tried to do quantum field theories not in Minkowski spacetime and define the dynamics through isometric embeddings between curved spacetime.
Yeah.
And so from what I got, I may be wrong, but the field is in this view is level 4 definable if you can define a suitable dynamics where there is a free evolution, which is something that might be nice. If you want to work with this. So
I don't know. I don't know. I mean, I see it again, the intuition, but I need to sit down and actually work through it. But yeah, thanks. I see the connection and I see the reason why you think that might be an equivalent way to say level 4. So why do you think that that's a mark in favor of level 4?
Because a field which is definable on a space-time would be definable. You wouldn't have to specify dynamics, right? There would be, I don't know, a notion of parallel transport in your dynamics without like interactions. It feels like it would be definable without the specification of a particular interaction, which seems
nice.
Which seems nice to be definable.
I'll think about it. Thanks.
So true. That's okay. That's okay. Then Ben.
Thanks for your talk. I'm wondering if you could say a bit about what's the difference between explicit and implicit defining.
Oh yeah, thanks. Good question. So, it's easiest to describe the difference by thinking about the first order logic case, or the case where you have a formal language. So in the first order logic case, some predicate in your language of your theory is explicitly definable just in case there's a formula you can write out using the other language in your theory, such that in every model of the theory, that predicate is equivalent to this more complicated formula that you could write out, possibly more complicated formula that you could write out using the other language of your theory. The intuition is like, you can just write out, like explicitly construct the new piece of structure from other structures. So like less than or equal to is explicitly defined in terms of less than. X is less than or equal to y. I'll give you the explicit definition, just in case x is less than y or equal to y. That's the explicit definition. Implicit definition, there are a lot of different varieties, even in the case of first order theories. It's something else, like that any change in the other structures results in a change in the new structure, ways of making that intuition precise. These invariance under symmetry conditions are one natural way to make that precise, but that's the main distinction. Is explicit is constructible from the other structures. Implicit is something else. Implicit notions are easier to work with in general relativity and outside the confines of first order logic because we don't have a formal language like what I was saying earlier, so they're easily exportable. And that's why we're struggling with the explicit stuff, because it's not as easily exportable because we don't have a formal language. Spencer?
If for condition 4, you strengthen, although I don't always remember which direction strengthen and weaken means.
Yeah.
Strengthen it so that you're not just talking about the injections or to embedding.
Yeah, smooth maps that
So
preserve the
single
metric.
maps that preserve metric.
Good
Is
question.
the same thing as explicit definability then?
No, you actually don't. We played around with this and it's a super headache. So a natural thing to do, this is a really good question. Thanks for asking. A natural thing to do is play around with what maps you're considering symmetries. Like don't just think about embeddings, think about any smooth maps that preserve the metric. The thing is that preserving the metric actually places super strong constraints on what a smooth map has to be like. And you don't strengthen level 4.
Really?
Yeah. So I was surprised by this. The idea is that like in category theoretic language, you actually haven't expanded your category at all. You've given a different definition of the arrows, but they aren't any different. So all smooth maps that preserve the metric have to be isometric embeddings.
Then they have to be injective.
Yes. Yeah.
Right. That's a big thing already.
Yeah. It's that
probably have a factorization system.
the metric
General
is just
case to a quotient followed by an embedding or something like that.
yeah. Yes. Yeah. Exactly.
Yeah, because it's like they all have to be rigid, all the maps. So you can't like move them.
Yeah. The idea, I mean, metric preserving is such a strong condition, is the thing. We were super surprised by this. Like, I thought that moving to level 4, now we were going to have a family of conditions here where you just change your naturality constraint in the second bullet. And I was like, that's going to be great. I mean, you do have a family. If you change this to just isometries, well, then you're at level 1 again. It's not good. But you can't get any higher here, or we haven't found a way to push up higher by trying to be more liberal about what constitutes an error in relativistic spacetimes.
Number 4 feels a lot like you have your category of spacetimes, and then you have another one that is the category of spacetime plus an extra structure that's preserved by the maps.
Level 4 is requiring that the projection functor is full.
Yeah.
That's an equivalent way of stating level 4. Yeah. And so you would think it's sensitive to the definition of the category.
Yeah.
And it is, but
doesn't matter.
Yeah, smooth maps doesn't give you a new category. Smooth metric preserving maps doesn't give you a new category. Yeah, so that's what I was hinting at when I was saying level 4 bears a close relationship to these bias, like category theoretic tools. That is the connection. Level 4 is super close to fullness. Sorry, go ahead.
Level 3 feels like it does as well. Like, have you looked at all at like whether or not level 3 can be phrased in terms of symmetries of sheafs on the space?
No, I haven't. I mean, the most natural. So, I'm sure all of these can be given like categorical clause. Insofar, I mean, they're talking about symmetry, so it's categorical clause and all that. It's just going to depend on what the category is that you're considering. At level 3, you're not going to be considering as many objects as level 4, right? Because you're just looking at the guys, yeah, exactly. This like smaller category. So I don't know. It's definitely not equivalent to the functor being full, though. Maybe, I should say, it's not equivalent to the functor from the enriched category of relativistic spacetimes once you've added the tensor fields beta to the original category being full. It's not that. It might bear some relationship, but it's not that.
Michael?
Yes, it seemed to me clear that your notion of explicit definability is essentially the same used in first or second order logic.
Yeah.
So
that's
not so clear that the notion of implicit definability is the same or similar. It seemed to me that what you call the implicit definability, is the fact that a given structure determine in a fixed way.
Yeah, the new one.
The new one.
Yeah.
Which is seem not exactly what is so it's enough to fix these parameters to have also this parameter fixed. It's not seem to me that is what is usually meant by implicit definability. It seemed to me that, of course, I absolutely not able to write your paper. Absolutely not.
Yeah,
But if I could have tried, I would possibly use the verb to determine rather than the verb to define. This is my first question.
Yeah.
Another one, but if you want to do the other as you want.
Sure, let me do this because I'll forget the things. So two things. So first on the explicit one, I'm not so sure that the explicit tracking is as close as you think it is. So like part of the issue with this was this is what I was trying to say earlier. Here, it's a close connection between explicit definability in the first order case and explicit definability here. If what you think the ingredients you have to explicitly define new things is just the metric. But we don't really think that. Like you think that you also have other ingredients. Another way to say this is like, we don't know, it's not just given to you and or maybe not given to me, maybe it's given to someone else, but it's not been given to me what the construction procedures, like the allowable construction procedures are on tensor fields on relativistic spacetimes. Like what can you do to the metric to arrive at explicitly defined new structures? Definitely you can do these things. Like you can take tensor products, you can take contractions, you can index substitute, you can take linear combinations, but maybe you can do more. So like in particular, you can write out explicitly the action of the covariant derivative operator on any tensor field in terms of the metric, but also Lie derivatives.
You answered to my second question.
Okay.
That is exactly what the point.
Great.
It seemed to me that the point that this notion of explicit definability is still very demanding.
Yeah, we've been straitjacketed here by the
exactly. And perhaps we could have an even stronger notion of explicit definability.
Yeah, in stronger in the sense that it's weaker. But better. Yeah. I totally agree. More expressive, allowing allowing more things to be definable, which is what we want because too few are now definable. Yeah, I totally agree. The only reason that we consider this one unit, like it's not a good candidate for an explication of notion of definability for relativistic spacetimes. It's way too. You can't do anything. The only reason we consider it is because it bears a close relationship to these varieties of implicit definability in some special cases. Like it is kind of wild that in Minkowski spacetime, level 1 is equivalent to this. It's not just equivalent to like a more liberalized notion of this where you allow yourself constructions using the covariant derivative or Lie derivatives or whatever. It's equivalent to this. And that's kind of wild. Like all of the level 1 implicitly defined tensor fields on Minkowski spacetime, you can build up with just taking the metric and like algebraic constructions of the metric itself. I found that like pretty surprising. That's the only reason why we consider this. It's not that we think it's a good notion of definability. It's just that in some cases, it's the notion that it's equivalent to the.
And this is just a question for pure ignorance.
Yeah.
So perhaps the question that I ask is totally absurd. When in logic we discuss about definability and non-definability, a question of cardinality is evident.
Yeah.
Something like that here?
Well, so let's see. All not
the Nike space is an Nike model, sorry.
Yes. So
is not the totality of the possible subset. So there is a question of cardinality there that is involved.
Yeah.
Here, explicitly definable means implied something in terms of cardinality or not?
I don't think so.
No.
Certainly not. It doesn't imply anything about cardinality of the underlying models that we're considering. I mean, they're all big and roughly the same size because they're locally isometric to R.
They're all separable spaces.
Yeah.
Small.
Big compared to other cardinalities that are small. You're right. They're not.
They're all inside the continuum.
Yeah, topologically they're small. Yeah, so I don't think so.
Okay.
It's just because the models of GR are all very similar to one another. in this sense, very different in other sense.
I'm wondering if the reason that level one and this coincide for Minkowski space-time has to do with the fact that the derivative is completely uncoupled from the metric. They're unrelated objects but for curved space, the derivative is covariant to the metric.
Yeah, that's well, okay, so it depends on what you mean by decoupled, because even in the Minkowski case, the derivative operator is compatible with the metric, in the sense that, like, the metric is.
I mean, it's trivial.
Yeah, so that's definitely a necessary condition, right? Because if, for example, your Riemannian curvature tensor didn't vanish, you would have no shot at strong explicit definability of every level one implicitly definable tensor fields. Or at least if it wasn't constant, you wouldn't have any shot, right? Because it is level one implicitly definable, but you can't build any non-constant stuff using just taking copies of its inverse and tensor product linear combinations or whatever. So it's closely related to something about the derivative operator, but I can't.
Yeah, I mean, if you throw in taking any number of derivatives into your tool set, that notion of strong
the resulting notion of explicit definability.
Yeah, I could see a path to that reducing to this one.
In Minkowski. Yeah. So that is like the next question. It's just a hard question. So the next question is like just trying to get a better notion of explicit definability by enriching our construction procedures that we can perform on tensor fields to construct new tensor fields, and then seeing how that's related to like level 4. So I can define a notion, but I don't know how it's related to level 4. I know that it entails level 4, but I don't know if level 4 entails it or not. So I don't want to talk about it. I don't have the answers to the questions.
Yeah, I think it's a good point to stop.
Thanks, everyone. This was awesome.